All right, guys, at this point, we should have already discussed the quantitative view of acid-base strength. So you should have an idea about how to use the pKa's of different acids to assess the relative strengths of those acids, and even then predict which side of an equilibrium equation would be favored based on the individual strengths of the acid. We'll get into this, just review it just really quickly in a second, but I want to introduce the topics that I'm going to talk about here in this next video. Most of the time, you're not really equipped with the pKa of the acid that you're looking at, and so you have to be able to have some sort of qualitative method in order to assess the relative strengths of different acids. You're going to have a set of things to look at. Briefly, you're going to look at the atom that the hydrogen is attached to. You're going to examine the resonance structures of the conjugate bases. You're going to take a look at the hybridization, what kind of orbitals the negative charge in the conjugate bases exists in. And you're going to take a look at if there's any inductive effects, the effects of electronegative atoms that are around that negative charge that forms in the conjugate base. For the most part, what we're talking about is figuring out a way to sort out the strength of an acid by really examining the relative stability of the conjugate base. And so the idea is that if an acid is strong, it means that its conjugate base is relatively stable. If an acid is weak, then that means its conjugate base isn't stable. And so let's get into it and let's take a look at some of those considerations that we would make in order to examine the relative strengths of different acids. Let me share my screen. We should go from here. Okay, so as I said before, you already should have some idea about taking a look at pKa's, and so let's just remember some of these pKa values. And now I wouldn't expect that you memorize every single possible pKa value out there, but there is a few pKa's that I think is really just beneficial for you to be familiar with. So if you take a look at some of these groups and you have a good idea of what their pKa's are, then you're in really good shape to begin discussing acid-base strength or acid strength and deal with that from a sort of quantitative perspective, even if you just know, say, these 1, 2, 3, 4, 5 different pKa values. And I probably should have arranged these two things, the water and the HCl. I should have arranged those differently since they have, that's the wrong order of strength. So let me put hydronium here and HCl here. And so what we want to do is we want to just talk about the relative pKa's, -7, -1.7. This is now, we're up to like around 16 here. Should have also then included water elsewhere. This is 15.7. That was very specific, and it's water, so you should have an idea about that. And then carboxylic acids are about 4.75. It might also be beneficial to think about what ammonia is. Ammonia is the highest one. It's 38. 38. Okay, and so let's think about this. One thing you want to be able to do is ask the question, you want to be able to answer this kind of question. Is sodium hydroxide a suitable reagent to deprotonate an average carboxylic acid? So which way is this reaction favored? So I would have sodium salt of the carboxylic acid plus water. Now, we should know the answer to this question, right? So you can think about it from a general chemistry perspective. You can say, well, sodium hydroxide is a base, carboxylic acid is an acid, acids base react, so this reaction should be just fine. Another way to look at it is to take a look at the relative pKa's, and the pKa was about 4.75 for this thing, and the pKa of water is 15.7. And so this is what we say. We say that in general, the equilibrium favors the side of the reaction that has the weakest acid. And so what do? If I have the pKa's, I'm armed with the pKa's, then I can take a look and say, well, 15.7 is higher than 4.75. So we could say that the water is a weaker acid than the carboxylic acid. And so that's the side of the reaction that's favored. Since the side of the reaction that's favored is the product side, then we say to ourselves, sure, sodium hydroxide is a suitable reagent to deprotonate the carboxylic acid, because when I write the reaction with that happening, I see that the equilibrium favors the products. And so that's what gives us this idea that, the reaction is favored. But what happens if I don't have pKa's? I mean, let's put those off to the side. One of the things that I want to be able to do is say, well, let me ask this question. Is sodium hydroxide, and at this point I want to get rid of sodium because you should realize that it's a spectator ion. It's not doing any chemistry. So I'm going to change the question. It's hydroxide. Is hydroxide a suitable reagent to deprotonate the proton on acetylene, on ethine? And so when I want to think about that in terms of the equilibrium, I would say, well, I'm still going to create water, but then I'd be left with an ethanide ion. So an alkanide with a negative charge on a carbon. And so, maybe the pKa is 15.7 for water, but here's the conjugate, the acid on the reactant side. What's the pKa of that? And again, you shouldn't have to memorize every pKa value in the table. You should be able to use a more quantitative understanding. Now, it turns out that this is actually going to be one of the exceptions to the order of importance, but we'll get into this one here in just a second. But before we do, let's take a look at some of the things that we would consider and how we would consider it. So let's just shrink this down, move it over to the side. Let's get rid of it for the time being, and let's think about what are the qualitative factors that we would look at. Now, these are the things that you want to consider. And generally, this is the order of importance. These are the four factors that you want to consider: atom, resonance, induction, and orbital. And remember, at the end of the day, what we're trying to think about, it's not in order to determine the strength of an acid, we're not really looking at the acid directly. What we're doing is we're looking at the conjugate base. So if I were to just show you a carboxylic acid, and show it losing its proton to do this standard Bronsted-Lowry acid-base equilibrium, then I have a conjugate base. And this is the conjugate base that we're examining, and we're asking ourselves, what's the stability of this particular species? And if we have two different conjugate bases for two different acids, well, that's not a good example since that's neutral. We can say we can compare the relative stabilities of these two species, and we can say to ourselves, well, which is the stronger acid? Is it the carboxylic acid or is it the water? Well, we know the answer because if you've already kind of sorted out the pKa's, you know the pKa of the carboxylic acid is lower than the water, and that's stronger. But how can we use these four factors over here on the left-hand side to identify which one of these things is actually stronger without knowing the pKa's? And so remember, this is the general order of importance, but this is going to, get you in trouble if you adhere to it without any other consideration to possible exceptions. Remember, if you just memorize the rules and you don't think about the possible exceptions, then you're going to miss some problems, because organic chemistry instructors love to put questions on exams and quizzes that are actually about the exceptions. And so that's one of the things you want to kind of wrap your head around. All right, so let's take it one at a time. Let's get rid of these. We'll think about it here in just a second again, but right now what I want to do is I'm going to look at the consideration of the atom. And remember, when I'm talking about the atom, what I really want to consider is what atom has the formal charge? What atom has the negative charge in the conjugate base? So let's take a look. What do you think is the stronger acid? Is it ammonia or is it water? If I were to think about how the individual species would donate a proton in a Bronsted-Lowry acid-base equilibrium, I would then take a look at the different conjugate bases and I examine the atom that holds the negative charge. So what we're going to say is that a negative charge is more stable on an atom that's more electronegative. So if I take a look at oxygen, I say to myself, it's more electronegative than nitrogen. So the negative charge is more stable on the oxygen than it is on the nitrogen. Because the charge is more stable in hydroxide than it is in amide, we're going to say that the water would be a stronger acid than the ammonia. And, we know that because one of the things we do know is that the pKa of that is 38, and the pKa of this is 15.7. And so, we know it from pKa values that indeed it is stronger. Okay, and so one of the things that I want to warn you about, though, is that when you're comparing the atoms, you only compare them on the same row. So you really only look at the period. So let's take a look at this one. Nitrogen, oxygen, and fluorine are all on the same row. And so we want to examine fluorine and say, if I wanted to compare ammonia versus water versus HF, then I can directly make that comparison based on the electronegativity of the conjugate bases. If I want to think about amide versus hydroxide versus fluoride, then I can easily say, I can succinctly say to myself, well, the negative charge is more stable on fluorine because fluorine is more electronegative than either oxygen or nitrogen. So we would predict that HF is the strongest of the acids. So as long as you're on the same row, of the periodic table, you can directly make this comparison. You also have to make sure that there's a charge, right? And so one of the mistakes I almost made earlier was to try to make a comparison between water and ammonium ion. But ammonium ion, when it donates a proton, forms a species that's neutral. And so the fact that there isn't a negative charge leads you into a totally different situation than when there is a negative charge. So I just want you to be careful of that. Okay, what happens if they're not on the same row? What happens if they're not on the same row? So let me, here, let's erase some of this. What if we want to compare water versus H2S? Now, these are in the same group, right? This is a group 16. Oxygen is above sulfur in group 16. So it's smaller, sulfur's larger, has more electrons. So if I were to just compare the atoms directly in the conjugate bases, I would say, well, oxygen's more electronegative than sulfur, so shouldn't water be the stronger acid? Well, it turns out, no, that's not the case. It turns out that this is actually the stronger acid. H2S is the stronger acid. So why is that? So this is where we get into the thing. You can only directly compare on the same row. Well, what's going on here between the two atoms, oxygen and sulfur? Well, it's the same sort of thing when I compared ethane versus pentane's intermolecular forces. It's the same idea. Ethane is smaller than pentane. So ethane has a higher boiling point because it has less dispersion forces, less instantaneous dipole moments. And so what this property is called polarizability. We would say that the pentane is more polarizable than the ethane because the electron cloud is larger. Since the electron cloud is larger, it's easier to distort. And if it's easier to distort, there's more of these instantaneous dipole forces. So it's a similar situation to this. But instead of a neutral molecule and van der Waals or dispersion forces, what we're talking about is a negative charge on an atom. In this case, we've got the sulfur atom versus the oxygen atom. I've already written that down. So which one is it more stable on? Is it more stable on sulfur or is it more stable on oxygen? Well, it turns out that it's more stable on sulfur. It's more stable on sulfur because it's larger. Since it's larger, the negative charge is more spread out. This means that it's more polarizable. Since it's more polarizable, the negative charge ends up being more stable. And so in summary, what we would do is we would say, if I'm comparing in different rows, I want to choose the atom that has the negative charge on the larger of the species. So even though oxygen is more electronegative than sulfur, the H2S is going to be a stronger acid than H2O because the resulting conjugate base is more stable. It's more stable because the negative charge is more spread out and thus more polarizable. And that's, from an energetic perspective, that's more favorable. Okay, so when it comes to atom, you're going to have two things to look at. But you can only compare things that are on the same row, and you can only make sure that you compare things that have a negative charge. So as long as it's on the same row, you're looking at the more electronegative atom. If it's on different rows, then you want the more stable species has the negative charge on the larger atom. All right, so that's it for atom. So we've knocked out atom. What's next? Resonance. And that's this same problem that we were working on before. What's the stronger acid? Is it water or is it carboxylic acid? Well, in this case, if I were to just consider what atom holds the charge on the conjugate base, I would notice that, well, they're both oxygen. So I can't use atom at all in any way to pick out what's more stable, whether it's the water or the carboxylic acid. I have to then take a look further down my list of considerations. And at this point, what I want to do is I want to consider the resonance structure. So is there resonance structures in the conjugate base? Remember that in general, what we're going to say is that a resonance, having a species that exhibits resonance and thus has delocalized electrons is more stable than one that doesn't. And so if the electrons are localized, they're less stable than electrons that are delocalized, as long as all other considerations are equal. And in this case, all the other considerations are equal. We're looking at negative charges on oxygen atoms. But there's a difference between the carboxylic acid and the OH molecule, or the OH ion. The OH ion does not have any sort of resonance where the carboxylic acid does. So if I were to show the resonance structure of the carboxylic acid, the negative charge can be on the atom pointing up versus the atom pointing down. And remember that the real structure is something in between. It's a hybrid of the two, where there's a partial bond all around and delocalized negative charge. This fact that the negative charge and the extra electron is delocalized is what leads to increased stability. And of course, remember, that's borne out by the pKa's, 15.7 versus 4.75. Certainly the carboxylic acid is a stronger molecule. Just be careful because there's going to be other considerations for where that might be. So if you take a look at something like, well, what about hexanol versus phenol? Which one of these is the stronger acid? Well, again, we're going to examine the conjugate base. With phenol, oops, I've got a negative charge on that oxygen. Let me back that up just a second. With cyclohexanol, I've got a negative charge localized on the oxygen. With phenol, I have a negative charge on the oxygen, but it's not localized. This negative charge can delocalize into the ring. And I can show a series of resonance structures that has that negative charge in a different location in the ring. And in fact, there's several resonance structures and several locations where that negative charge can be shown. We can show one more. And then I could go back to the original conjugate base by showing that movement there. And what we've done is it looks as if we've moved the electrons around the ring. Remember that if it's got a resonance structure, then that means that the truth lies somewhere in between. And so the electrons in the phenoxide ion are definitely delocalized in the ring because of the resonance, and that leads to greater stability. If you take a look at this, is a pKa of 9.9, essentially 10, where generally alcohols have a pKa approximately 16. So that's quite a bit stronger of an acid. And so resonance does play an important role when it comes to the relative strengths of acids. And so you want to be sure to consider that when you're taking a look at different structures. All right, so let's take a look. What about one more example with resonance? How about something like this? What's a stronger acid? CH3, CH2, NH2 versus CH3, NH2. So I have a simple amide versus an amine. Which one's a stronger acid? Well, if I take a look at the conjugate bases, in this one, I have the negative charge on a nitrogen, and in this one, I have the negative charge on a nitrogen. Still two lone pairs over here as well. Well, is there a reason why one of these structures, even though they both have negative charges on the nitrogen, should be more stable than the other? Well, this one has some resonance ability. And so I can draw a resonance structure that shows the electrons on the nitrogen can delocalize into the carbonyl group. And I now have moved the negative charge onto the oxygen atom. So here I've got the negative charge appearing on nitrogen in both cases, but the fact is that resonance shows me that the charge is shared with the oxygen atom. The electrons are delocalized. So this one is the stronger acid than this one. And so that's another example of how resonance can play into your consideration. Okay, and so what about, so that gets us taken care of for resonance. What about induction? Well, let's take a look at something like this. CH3, CH2, a 3-carbon carboxylic acid versus something like this. CH3, let's do CH2 with a Cl, CHCl, OH. So now I've got two of these guys, and the only difference is that one of them has some chlorines attached to it and the other one doesn't. So at the bottom, I'm still wanting to, we're still going to examine the relative strengths of the conjugate bases. So it's this one versus and I'm going to get it all nice and condensed, this one. Well, look, they're both negative charges on the oxygen atom. So we're not going to look at the atom to decide. They're both from carboxylic acids, and so they both have resonance structures. So we can't use resonance structures to make the decision on whether or not the atom, whether or not the species is a stronger acid. We have to look at this idea called induction. And induction is, how does the acid strength of a molecule affected by the presence of other electronegative atoms in the molecule. So I've got a chlorine attached to that carbon. I've got a chlorine attached to that carbon. I don't have any chlorines in that molecule. So how does that affect it? Well, remember that chlorine is an electronegative atom. And the more electronegative the atom is, the more it withdraws electron density. And so the basic idea is that we're going to sort of use the same concept from resonance, right? The more delocalized the electron is, the more delocalized the negative charge is, the more stable it is. Now, we're not going to be able to show induction with arrow movement and pushing of electrons. We have to just sort of invoke in our minds this concept of electronegativity. In the species on the left, yes, the negative charge is delocalized between the oxygens. But in the species on the right, not only is it delocalized between the oxygens, but the presence of the electronegative chlorines withdraws electron density away from the carbon-oxygen part of the molecule, and thus further delocalizes the negative charge towards this side of the molecule. And that's going to provide additional stability, making this species the stronger acid. And so in general, the more electronegative the atom that is attached, the more pronounced the effects are. And in addition to that, the closer the atom is to the negative charge, the more pronounced the effects are. So if I were to take a look at even something that doesn't have resonance, let's take a look at an alcohol. If I have CH3, CH, Br, C, OH, and I want to compare it to CH2 with the Br at the end, the same number of carbons, all of the same other atoms. Well, which one is the strongest acid in this case? Well, if I were to look at the conjugate bases, remove the proton and show this species with a negative charge, I have an electronegative group for both of them. I have a bromine on that carbon and a bromine on this carbon, but this bromine at the top is closer than the bromine at the bottom to the negative charge, so the inductive effects are larger. And so the species on the top would be the conjugate base that's more stable, leaving its conjugate acid as a stronger acid. And so that pretty much takes care of induction. And so now what we have to do is we have to look at orbital. How does the orbital play into this? Well, I think it's instructive to show you, based on pKa values, that this bears out. So we'll mix up pKa values, and we're gonna show you, and we're gonna think about it qualitatively as well. So what we're talking about is what is the hybridization of the orbital that holds the negative charge? What is the hybridization of the orbital that holds the negative charge? Let's look at ethane versus ethene versus ethyne. If I were to think about all of the conjugate bases, then I'm left with the negative charge on a carbon atom in both cases. So I'm still, at the end of the day, I'm still thinking about which one of these conjugate bases is more stable. Because the more stable the conjugate base, the stronger its conjugate acid is. And so what we want to think about is this. We want to think about where the electrons that are resulting in the conjugate base, where they reside from an orbital perspective. In this case, in the very first case, they reside in an sp3 orbital. In this case, it's an sp2 orbital. And in this case, it's an sp orbital. And so what do we know about sp3, sp2, and sp orbitals when it comes to how close they are to the nucleus? The sp3 orbital is furthest away from the nucleus, then the sp2 orbital, then the sp orbital being closest to the nucleus. And the idea that we want to invoke in our minds at this point is that the closer the negative charge is to the positive charge of the nucleus, the more stable it is. So the closer you let that negative charge get to the nucleus of the atom that has that negative charge, the more stable that negative charge will be. And you can think about that from an electrostatic potential, where the charge separation determines the potential energy. The larger the charge separation, the larger the potential energy. So thinking about species being more stable is the same as having lower energy, then we would conclude that the ethine would be the strongest acid, followed by the ethene, followed by the ethane. And if we look at the pKa's, we see that the pKa of ethane is 50, of ethine is 44, the pKa of, or excuse me, ethene is 44, the pKa of ethine is 25. And so when you think about the differences in acid strength, ethene is about 1,000,000 times stronger than ethane. But ethine is so much stronger than ethane, it's 25 orders of magnitude. I don't even have a name for that. Again, can't say 1,000,000. The difference here is 6 orders of magnitude, 10 to the 6th. So I do have a name for that. That's 1,000,000. The difference between ethene and ethine is what? 11 orders of magnitude, 10 to the 11th. So that's like 100 billion times stronger than ethene. That's how much stronger ethine is as an acid. Now, the pKa is 25, right? So compared to water, it's not really a strong acid. But with the pKa being as low as it is, 25, it does end up having some acidic properties. And there are bases that are strong enough to deprotonate that molecule and actually form the alkanide ion. This is the negative charge of the alkyne is an alkanide ion. And so this is how orbital is affected here. So we take a look generally at the orbital, and the sp hybridization is more stable than sp2 hybridization, which is more stable than sp3 hybridization. So now that we've taken a look at all of those things, let's start to ask ourselves some questions in the realm that we were just talking about. So one of the questions that I asked was, is sodium hydroxide a suitable reagent to deprotonate acetylene? Well, we do know the pKa's, right? We know the pKa of this one is 15.7. We know the pKa of this one is 25. But let's pretend that we don't know that for the moment. Let's take a look here. And I'm going to get rid of the sodium because remember, it's not doing any chemistry. All right, so now I've got my 2 conjugate bases. Which one of these conjugate bases would be more stable? Well, at first glance, what we're going to say is well, the oxygen being on the same row as the carbon is more electronegative And so it's going to be more stable. And so we would say to ourselves, okay, that's more stable. Since the hydroxide is more stable, the equilibrium favors the reactants and not the products. And so in this case, we would say this is not a suitable reagent. And again, this is borne out by the pKa's. The pKa of this is 25. The pK of this acid would be 15.7. And we say that the equilibrium favors the side with the weaker acid. And so in this case, the equilibrium favors the product side, 25 larger than 15.7. So everything is working out fine for us there. Well, let's take that a step further. Let's examine another situation. Is amide ion a suitable reagent to deprotonate ethine? And so I want to examine the resulting structures. I get ammonia, and I get this alkanide ion. And so this is where I'm going to warn you, right? Because if you just follow the rules blindly, then you're going to come to the same conclusion. You're going to say, well, nitrogen is more electronegative than carbon. And because nitrogen is more electronegative than carbon, you'd like to say to yourself, well, this one is more stable. And so that means that you would consider that the equilibrium probably favors the reactants again. And so you're saying to yourself, no, amide is not a suitable reagent. But this is really where the pKa's are important. Is amide really stronger, or is amide really more stable than the alkanide ion? Remember, what's the pKa's? 25 for that acid, and it's actually 38 for ammonia. And so if we use, we do have the pKa's in this case, and so here's one of those exceptions, right? And so yes, amide is a suitable reagent to deprotonate ethine, because the weaker acid actually lies in the products and the reaction favors the product side. And so the answer to the question is yes, but if you were to just blindly follow the rules, you would come up with the answer no. And so again, I'll just warn you, don't always blindly follow the rules, because you're going to, get in trouble sometimes that way. So let's take a look at one other example before we kind of move on from here. Let's do this one. Is water a strong enough acid to reprotonate a carboxylate ion? Is water a strong enough acid to reprotonate a carboxylate ion? So can I just mix carboxylate ions in water to reform the carboxylic acid? And so let's take a look at our conjugate bases. So in this case, I've got a conjugate base with a negative charge on an oxygen. And in this case, I've got a conjugate base with a negative charge on an oxygen. So I have to continue to think about the different possibilities. Well, the next thing to think about is resonance. Is there resonance in one of these species or the other? And the answer is yes. I've got some resonance here I don't have any resonance on the hydroxide ion. And so this would lead me to believe that this is more stable. And so if I have a species that's more stable in the reactant side, then which way does the reaction actually favor? Does it favor the reactants or does it favor the product? Well, you know, it's going to favor the side that has the most stable species. And so the answer to the question is no, water is not a suitable reagent to protonate a carboxylate ion. And you can check your work by going back to the pKa's, 15.7 and 4.75. Water is clearly the weaker acid, and so the equilibrium favors the side of the reaction that has the weaker acid. And so water wouldn't be sufficient. Well, let's think about something that would be sufficient, right? Like, is there something that is sufficient? Well, what about amide ion? Is amide, oh, excuse me, is ammonia, not ammonia, not amide, but ammonia. Is ammonia a sufficient reagent? Is it sufficiently basic to reprotonate? Oops. The carboxylate ion? Well, let's take a look. Which one is more stable? Again, we're going to come up to this idea that the oxygen is more stable over the nitrogen because of electronegativity and the fact that there's resonance in the structure here. We still think this is more stable. So yes, ammonia is something that can donate and accept protons, but it's not strong enough as a base. Excuse me, it's not strong enough as an acid to reprotonate carboxylate salt. And we can, again, bear this out with pKa's 4.75 versus 38. It's a lot more favored to the reactant side. But what if I were to switch it up and use something like, what if we were to use something like actual hydronium ion? Is hydronium sufficient to reprotonate the carboxylate? Well, what do we got here? I've got, I can't really use, in this situation, I really can't just go atom, resonance, induction, orbital. And the reason is that I have charged species here and I have neutral species here. So remember that you can really only make comparisons as long as the value of the charges are the same. So if I were to say, okay, here's the acid, here's the base, here's the conjugate base, and here's the conjugate acid, I can't compare the relative stabilities of the two conjugate bases because one of them is charged and one of them isn't. But again, if I go back to the pKa's, negative 1.7 versus 4.75, the equilibrium would favor the products because in this case, the weaker acid is on the product side. So we can go back to the pKa values every time and figure it out. In general, if I have the less formal charges that I have, the more stable the species are. This is the same as we thought about when we discussed the relative importance of resonance contributors. The same thing is going to be generally true with acids and bases. And so in this case, hydronium would be a suitable reagent to reprotonate the carboxylate ion. All right, and so that's the last little piece there that I want to go with when it comes to acid base strength. But that strictly takes us out of, that ends our discussion about Bronsted-Lowry acids. And so what I want to do is I want to switch up and I want to talk about Lewis acids and Lewis bases. Remember that the Bronsted-Lowry acid-base definition talks about the donation of a proton. If a proton is donated and comes off, then this is how we think about in terms of Bronsted-Lowry acids and bases. But what about this reaction? Is this an acid-base reaction? And if so, is it a Bronsted-Lowry acid-base reaction? And the answer is it is an acid-base reaction, but it's not a Bronsted-Lowry acid-base reaction. It's actually a Lewis acid-base reaction. And so Lewis acids and bases, instead of talking about things in terms of a proton being donated and accepted, it's actually in terms of electrons. So a Lewis acid is an electron pair acceptor and the Lewis base is an electron pair donor. And in all of these Lewis acid base reactions, we have bonds formed. And so let's take a look. What's happening here? The chlorine has lone pairs that are attacking the iron to form this new covalent bond. And so this is an example of a Lewis acid-base reaction where the lone pairs from the Lewis base are donated to the Lewis acid and a new bond forms. And so that's really all that you need to know about Lewis acids and bases. And so what I'll do is I'll just stop there and I'll just say the next thing. Lewis acids and bases really make up the heart of the majority of reactions in organic chemistry 1. And so after we stop talking about Bronsted-Lowry acids and bases, we're going to spend most of our time talking about reactions that at their hearts involve what things that you could call Lewis acids and bases. That doesn't mean that Bronsted-Lowry acid-base chemistry isn't going to be important. There's going to be a lot of things that involve proton transfers, and of course then a proton transfer would be a Bronsted-Lowry acid-base step. But by and large, the heart of most of these reactions involve Lewis acids and Lewis bases. And so that's what you need to be able to do there is identify whether or not an electron pair is being donated, whether a proton is being donated, or whether maybe you could even call it both ways. So I'm going to sign off today. That's going to be it for the acid bases part. What I'll do is follow up again and we'll start talking about alkanes.